Hi everyone, my name is Jordan and I'm the team leader of this group. Today me and my teammates are going to explain how a regenerative braking system works by using Faraday's law and Lenz's law. To start off this video, I'm going to give you a brief introduction on our given topic, which is regenerative braking system. Every time you step on your car's brakes, you are wasting energy. So when your car slows down, the kinetic energy is converted into waste energy like heat. Is there anything that you can do to stop wasting energy? Not really, because heat energy is an inevitable byproduct of braking. However, some engineers have come up with a kind of braking system that can recapture much of the car's kinetic energy and convert it into electricity, which can be used to recharge the car's batteries. This system is called regenerative braking.
For this video, I'll be talking about Faraday's law. So, what is Faraday's law? Faraday's law is the amount of EMF induced in the circuit, which is directly proportional to the rate of change of the magnetic flux through circuit. So, for now, just ignore this image. I'll be introducing the equation instead. For the equation, it's EMF equals the number of turns times the delta phi divided by delta time. So it means that the initial phi minus the ending phi over the initial time minus the ending time. So the negative here means Lenz's law. So we can choose to completely ignore this for the Faraday's law because it's not really important for now. There is another formula for the calculation of magnetic flux, which is also known as phi equals BA. B meaning the external magnetic field, while A equals the area of coil. That is all, and I'll be using a stimulation to show how Faraday's law works. Thanks. Stimulation for Faraday's law. So I enabled the field line so that we can clearly see what's going on. So if I were to take this magnet and cut through the coil, voltage will be expected. So if I were to put the north one inside this coil, a negative voltage will be produced. So I'm just gonna go in real quick. As you can see, when north enter, the voltmeter flickers. Let's see. So if I were to do it faster, I can voltage keeps cutting and we can keep seeing it. But if I were to make this stay here, the voltmeter will go back to 0, which means there must be energy produced. So if there's nothing to push it around, the voltmeter won't flicker. So, but if I were to use a bigger coil, I can see that the voltmeter will flicker more to the left. So just to prove to you guys, see, it went all the way back down, and right here it went all the way back to the right. Same if I just switch the direction, the positive will go down and the negative will go down for like a different sequence. So this means that if there is more coil, when the magnetic field cuts through it, more voltage will be produced. And if the lesser the coils, lesser voltage will be produced. And the other important tip is when it goes faster, the voltmeter will go faster as well. So that is all. Yes, it's me again, and I'm here to introduce to all of you to Lenz's law. So for this, we're not going to talk about the equation where it negative n delta 5 over delta t. We're not going to talk about this for now. So instead, we're going to use the conservation of energy to explain to all of you guys. So I assume that all of you know that energy cannot be created or destroyed. It can only be converted, transformed, whatever you guys want to call it. So for example, you're driving. So all of us know that when you're driving, kinetic energy and friction exists. The friction exists because of the tire. But what exactly is friction? So for this case, friction is the opposing force, meaning it's trying to pull back the car. But then, also heat energy also exists from here. So how did heat energy come from? Since heat energy cannot be created or destroyed from other, that means it can means that kinetic energy is converted to heat energy, but not all of them is converted. So that means when the kinetic energy decreases, the amount of kinetic energy that was decreased will be converted to heat energy. So let's take this logic and put it for Lenz's law. So in this solenoid, the voltmeter, assume this is zero. Assume this is zero. So if you were to put a magnet inside, according to Faraday's law, you'll know that the magnet will the voltmeter will flicker. This is because the electrical energy is converted from the decrease of kinetic energy. So to go in more depth, that this is because of how the current flows. The current will flow in a direction of which it opposes the motion of the magnet. So repulsion force is over here. So when that occurs, electrical energy also occurs. But electrical energy is converted from the decrease of kinetic energy. So going back to for the next video, I'll be explaining about eddy current.
Alright, that's it. That's all I want to record. This is how it happened. That's all.
I assume that all of you have watched me playing the steel ball at the magnet. So, what is eddy current? Eddy current is created because there's a change in the magnetic flux. In this diagram, we can see how the eddy currents are formed. So, if you watched the video just now, you can see that when the steel ball drops, the metal tube drops from the metal tube, it goes down very fast. But however, when you use a magnet and when it's falling down the metal tube, it can be seen like something like this image over here. So it means it goes down slower compared to a steel ball. So why is that? This is because when the magnetic field line cuts the metal tube, an EMF is produced, or electromotive force. So the EMF will then cause a current. This current will create a magnetic field which opposes the magnet's fall. So as you can see here, the current will get opposed. Thus, when it's falling down, so it'll be going down. But then the current will oppose it, trying to make it go up. But then eventually the metal will fall down. So this circulation motion over here is also known as eddy current. So that is all.
In a regenerative braking system, the electric motor has dual function. When it runs as a motor, it converts electric energy supplied by the batteries into kinetic energy which drives the wheels. However, while braking, it runs in the opposite direction and becomes an electric generator. It converts the loss of kinetic energy into electrical potential energy. This is why it is also known as a kinetic energy recovery system. When brakes are applied to an electrical powered vehicle, electric supply from the batteries of the vehicle is cut off from the electronic system. Due to inertia, the remaining kinetic energy makes the wheels turn and subsequently turns the coil inside the motor, which produces a negative torque. The motor will now work as the generator. As the wheels are moving, the metal plate of the wheels will cut the magnetic field lines of the permanent magnets. According to Lenz's law, the EMF induced moves in a direction that opposes the motion of the wheels. Eddy current induced in the metal plate of the wheels will produce a brake force that opposes the direction of the wheels, powerful enough to slow down the vehicle. According to Faraday's law, the rate of change in magnetic flux results in an induced EMF in the coil and produces electric current. This tells us that the faster the car is moving, more current will be generated because the rate of change in magnetic flux is faster. The current will flow from the electric generator back to the batteries, charging them up. In a nutshell, Lenz's law explains how the brake force is generated, while Faraday's law explains how the system generates current. Here are some videos that may help you to visualize a regenerative braking system. As you can see, when the driver steps on the brake pedal, the permanent magnet gets closer to the wheels. Due to change in magnetic flux, the wheels stop moving and the bulb lights up, which shows that current is produced.
Thank you.
Here's another video that shows the effect of permanent magnet on a moving metal plate, which can use to represent the wheels.
Hey guys, I'm Yoong, and I'll be talking about the pros and the cons of regenerative braking, mostly in vehicles such as this one, the Toyota Prius, one of the world's ugliest cars to me, and also in locomotives such as this one, also known as a train. So starting off with the advantages, firstly, the motor takes in the electrical energy from the battery and then converts it into the mechanical rotation of the wheels. This means that as you brake, the kinetic energy is converted into electrical energy, which is then stored inside the battery to be used to power the wheels. In addition, it helps to improve the fuel economy of the vehicle. That means the car uses less petrol. And not only that, there will be less carbon emissions emitted, which makes it more eco-friendly. Furthermore, it prolongs the charge of the battery. When the energy is captured by the regenerative brakes, the energy is stored into the system, later then reused as energy to the battery. And lastly, there will be less wear on the conventional braking system. So as you guys may or may not know, regenerative brakes work in conjunction with conventional friction brakes. When these two brakes work together to slow down the vehicle, there will be less wear on the conventional braking system on parts such as brake pads and brake discs, and will be able to last longer. So now, on to the disadvantages, the not so good stuff. So firstly, it adds complexity to the brake system. So with two braking systems, comes with more moving parts, which means that there are more parts which can fail. In addition, the regenerative braking system still relies on the conventional friction braking system, as its braking effect decreases as speed of the vehicle is increased. This means that as the car is traveling at a higher speed, as you press all the brakes, not all the kinetic energy will be converted into electrical energy, which can be seen down below in the graph. And this is because the charge should be too high for the battery to absorb. Which brings me to my next point. Deceleration rate is limited to prevent battery damage. Moving on. Long distance driving will not see the good effects of regenerative braking, as there is very little braking involved, as compared to city driving. Moreover, energy can be lost in the form of heat as the current travels through the resistors, and not all the energy gained from braking is used to power the motor. In addition, cost of components, engineering, and manufacturing will make the car less affordable. Especially with our technology right now, the cost of production for components, particularly the battery, is still very expensive to produce. And lastly, toxic gases such as hydrogen fluoride and phosphorus fluoride are emitted when a battery pack combusts. So in the case that the battery pack has been punctured and the safety features fail, the combustion of the battery pack will produce hydrogen fluoride and phosphorus fluoride, which are highly toxic and need special firefighting techniques to put out the fire.
There are multiple applications of regenerative braking. For instance, the most common example existing in hybrid vehicles such as the Toyota Prius and the Tesla Model 3. When the accelerator pedal is not pressed, the car will automatically slow down because of the regenerative braking system. A percentage of the kinetic energy from the tires will be converted back into electrical energy and stored in the battery. This feature is very useful in stop-and-go situations such as on public transportations in the city. Most electric trains utilize this system as well. For example, Germany's first hydrogen-powered train has implemented this technology into their design, which will save more electricity while also greatly reducing pollution. It can also prolong the lifespan of its brake pads, which are applied in case of an emergency. Aircrafts have tried to incorporate this regenerative braking system as well. The energy can be stored during landing and used when it's taxiing. Pretty simple concept. However, there's too much kinetic energy when the tires come in contact with the ground, which is difficult for the regenerative braking system to recover. This makes it not very cost efficient as only a small fraction of energy is stored. Very few electrical bikes have regenerative braking. Some examples of e-bikes with regenerative braking include Stormer's ST2S and Ohm Cycle's City 500. Although it may seem beneficial, it is actually impractical and inefficient to do so. This is because a direct drive motor is required, which most bikes don't have, and the energy recovery is typically only around 5%, which isn't a lot because of how seldom you brake. Although this might not be applicable in reality, there are a few things to consider to improve the regenerative braking system. Since it relies on an AC generator, we can use the formula EMF equals to the negative of the number of turns multiplied by the change in magnetic flux divided by the change in time. This can be rearranged to become EMF equals to the negative of the number of turns multiplied by the magnetic flux density, the width, cos theta, and speed. Thus, to increase the EMF induced, we can increase the number of turns of the armature coil, use a stronger magnet, increase the width of the armature coil, and increase the speed of its rotation.